Everybody, my name is Mr. Rich. My email is richv@uei.edu. My phone number is 323-631-9494. And today's date is October 23rd, 2024. We are going over motor control, EL21-170. Today in particular, we're talking about Unit 2, Day 1. The objectives of the day are identifying contact relays for motor control and load matching. We go over the materials and the different components that we need in order to control a motor through a contact and a start-stop switch. So the lab equipment we need is a 120 to 24 step-down transformer, a 24-volt coil starter, or in other words, magnetic starter, and we have a 3/4 horsepower single-phase motor, a start-stop push button, and a lamp. Now the materials we will need is 14 gauge copper, THHN, thermoplastic, heat nylon, metal wood screws, and wire nuts. So we come over here. This is our setup for motor control. So now I'm going to describe all the different components that make up this system. So here is our single phase 120 volt motor. This is rated at 3/4 horsepower, indicated here on the nameplate. Here you got one phase at 60 hertz frequency. This is a 1760 RPM motor. So now this is the wiring diagram that we follow in order to hook up our lines 1 and line 2, which is our neutral. Now this is a terminal block that we use to connect our power through a pit cord. We use 14 gauge for this. Now this is our step-down transformer. In order to turn on the coil, or in other words, run voltage through the fixed contacts of this magnetic starter, we have to turn down the voltage or step it down from 120 to 24 using a transformer. Now, since this contactor relay does not have a normally open auxiliary terminals, we improvised by hooking up pins 3 and 4 from the push button in parallel with the normally open rails here. These are the contacts for the coil, which are running from the 24 volts supplied by the transformer. Now the idea is if we push the start button, this turns on the coil, which becomes an electromagnet, or in other words, a magnet. So now the latch runs voltage from this contact down to the motor. So now here's some key importances. So we have to do load matching. So in order to match the load, we have to make sure that our contactor is rated for the load ampacity of the motor, and it can handle the voltage that we are also supplying to the motor. So in order to do that, we need to look at table 430.248 in the NEC. Table 430.248 goes over full load ampacities given a voltage. In this case, we have a 3/4 horsepower motor at a 120 volt AC. So using the table on 430.248 for single phase motors, here we can see that the full load ampacity for a 120 3/4 horsepower is at least 13.8 amps. This tells us that we need to at least have a contactor that's rated at 13.8, or it can handle 13.8 amps. Experimentally, this motor draws about 4 amps using a digital multimeter. This table here accounts for not just one brand of motor, but multiple. So now you can go over additional methods for fuse selection, short circuit protection, and ground fault protection using full load ampacities. So there's an additional chart that will be discussed later on how to select fuses and how to select breakers in order to handle that full load ampacity for this motor. So now, let's get to it. So we're going to use a multimeter to measure the current, and we're also going to connect our power cord or power supply and then turn on our circuit. So here we go. We have 120 volts coming in from the outlet. We have our start stop push button. So turning this on, it stays on because pins 3 and 4 are in parallel with the normally open contacts here. The coil is then becomes a magnet, so then that attracts the magnetic core of the contactor. Now we are able to run 120 volts from the source or outlet down these fixed contacts to the motor. Now additionally, we have a lamp that's in parallel with the motor because they both operate at 120 volts. Now here we're going to go over amps. So we're going to measure the amps or the ampacities of the motor. So let's see how many amperes we get. Alright, so it says here that we're drawing about 2.5 amps. Alright, let's do that again. So here we're drawing 3.8 amps. As you can see here. This demonstrates Kirchhoff's current law. Whatever is drawn from the source is basically being outputted by that neutral. So here we have the stop. So once you push this button, the normally closed button, your system turns off.
Yeah. Open this and explain the diagram.
Sure. So right now we're gonna explain how the internals look on our push button. Okay. So we're gonna go over what we need from our tool bag. So this is your tool bag here. So in order to remove these 632 screws, we're gonna need a Phillips screwdriver. It's important not to use a power drill as that can strip the hardware. So first, before working on anything, we're gonna make sure that this is de-energized. So again, the 120 volt source is stepped down using a step down transformer from 120 to 24 volts. Then we can turn on this magnetic starter because the coil is rated at 24 volts. It will not turn on anything lower than that. So now here we have 4 different pinouts. Okay. So we have pins 3 and 4, which represent the normally open contacts for the push button. And down here you have your normally closed push button. So now from the source, you're feeding in 120 volts into pin 6 of your normally closed. Now pin 6 and 5 are connected because they are normally closed. Now we have a jumper wire here that connects to pin 4, but pin 4 and 3 are normally open. So voltage will run from pin 6 to pin 3 only if the start is pressed. Now, pin 3 and pin 4 are in parallel with your normally open contacts here. There's a spring inside that becomes actuated as soon as you energize the coil. So now, this is the 120 volt source that's feeding in through this contact, and when the coil is energized, this presses down. Right now it's de-energized, so it does this. Now voltage runs through here. Okay. Yes. So this is in parallel with pins 3 and 4. These fixed contacts are able to supply a higher voltage rating than the coil itself. This is how we get 120 volts feeding into both the lamp and our single phase motor. So normally when we press the start button without having a parallel configuration with pins 3 and 4 across these fixed terminals, you will have to hold the start button. But the good thing is if we hook these up in parallel with pins 3 and 4 are normally open, once we press the start, this turns on and you don't have to hold the button. Now 120 volts feeds in from this contact, and that's what powers this lamp and this motor here. Now, problems that may occur. Sometimes you have terminals that disconnect. Okay. We're going to demonstrate that here. Maybe loose configuration such as this. We can see now what would happen.
Testing.
So now we have a loose contact which can represent or simulate a fast-paced environment, or not paying attention to your work. So now let's see what happens when we disconnect one of the pins from 3 and 4 across this normally open contact here. So normally we would leave it on, but because we don't have this terminal in parallel here, the push button will not work. Now we're gonna reinsert this into here so that we can see the importance of having a parallel voltage running across your normally open contacts here. So all we did was connect pin 4 to this fixed contact, and then pin 3 remains in contact up here. All right, here we go. All right, let's see what happened here. Let's make sure that all our contacts are secured. Oh, here we go. So now we have a loose contact here. So this is part of your troubleshooting. You gotta figure out what went wrong, right? Here we go. Do a pull test. Make sure everything's secured. And there we go. There we have it. All right, so we went over the basic fundamentals of contactor selection, the importance of load matching, why it's important to look at 430.248. Without that chart, we might mismatch a part. Okay, if you choose a rating that's either higher or lower, that can make all the difference. So that's why it's important to follow the manufacturer's data sheet in order to see the capacity it can handle for every device and the voltage it can handle.